Before we get started, I need to go over a few housekeeping matters. First, I'd like to thank our funders for making this workshop possible and free for participants. So a big thanks to Northwestern Energy and the Northwest Energy Efficiency Alliance. The next thing I need to go over is that education credits will be available for this. To get those credits, you will need to attend the entire workshop. And then afterwards, if you would send an email to Tracy Collett at the Montana Bureau of Labor and Industry, she'll supply the certificate for your continuing education credits. If you would also, please CC me at the email addresses that you have on your screen. And from time to time, I'll at break time, we'll put this back up so you can make sure that you have those email addresses. We want this to be an interactive workshop and we want your participation. So throughout the workshop, feel free to ask questions, and there's several ways you can do that. On your screen, you may have to hunt for it, but you'll have a virtual way to raise your hand. So if you do this, you have a question and you want to ask at that point, raise your hand and I will call on you, and then you can unmute your microphone and ask Jaya your questions. If you would rather, there's also a chat function on your screen, and you can, I'll be monitoring the chat function. You can type your question in there, and then I will ask Jaya your question directly. The workshop is scheduled to have about an hour break time, but I think we're going to tighten that up a little bit because we want you to get out of here at a reasonable hour, and we want to make this as painless as possible time-wise. So as you're going through the process, just make sure your microphones are on mute, and you can leave your cameras on or off as you wish. So without further ado, I'm going to turn this over to Jaya for her presentation.
All right. So as the title suggests, this report aims to develop the Commercial Code Enhancement Plan for Montana, which is part of the Commercial Code Enhancement Initiative promoted at NEA. And as many of you may already know, the main objective of the CCE initiative is to assist adoption of advanced design and construction practices in mainstream commercial building industry. So the objective of this report was to assess high-performance technologies that are applicable to Montana. And before I begin, I would like to acknowledge that this presentation was made possible with the Northwestern Energy University Benefit Funds. Okay. So here's the overview of this presentation. I will start by describing the overview of the Commercial Code Enhancement process as envisioned by NEA. I will then briefly go over the roadmap for the reports that we had prepared for NEA, in which I will be presenting the procedure that we followed in selecting high-performance buildings, as well as selecting high-performance systems. After that, I will be presenting case studies of high-performance buildings in Montana that we considered for this report. And those slides will be followed by a discussion on high-performance systems, where I will be presenting our evaluations of these systems in terms of their characteristics, in terms of their application and suitability for the market and energy code. And finally, I'll be presenting the summary of these evaluations. So let me start with an overview of the CCE, or Commercial Code Enhancement Initiative. And NEA is deeply involved in the Northwest Commercial Codes market through its existing codes program. And it provides funding that goes to support state infrastructure, code change analysis, code policy development on a regional and national level. So for that purpose, NIA is in the process of designing the Commercial Code Enhancement Program, or the CCE program. And the CCE adds dedicated strategic and operational resources to NIA's current codes effort. The CCE initiative also aims to bridge this gap between current market practices and state policies, and it does so by identifying, by assessing, and by validating the feasibility and the affordability of next generation technologies and practices for commercial code construction. So to ensure that the states in the Northwest adopt these efficiency opportunities, the CCE initiative identifies and validates technologies and practices, and then works to build market awareness, to build capability and support for new associated code measures. And the way CCE works is that this effort is supported or informed by regional utilities and energy efficiency organizations, and also by code experts and market partners. And these agencies work together in tandem to identify and to tackle major market barriers to code change. Now, one major barrier to adoption of next generation technologies is the lack of awareness of benefits these technologies have to offer. So this initiative works to address these awareness barriers by demonstrating cost effectiveness and feasibility through case studies, through technical analysis, and through outreach efforts such as this one. So to address the issues of major market barriers to code change, Ideal Bozeman compiled a report that identifies several high-performance buildings that have been constructed in Montana. And the report also identifies several advanced HVAC technologies that are implemented in these buildings, which include technologies for air distribution and controls, hydronic distribution, central equipment, motor control, and performance monitoring. Now, the report then describes each of these selected technologies and provides a scorecard which rates the technology in terms of marketability, in terms of savings potential, and acceptance by the utility programs. So the screen or the slide that you see in front of you is the proposed, was the proposed roadmap for this project. So in the first step of this project, we wanted to consider all the high performance buildings in Montana and to see what makes these buildings high performance. So here's a list of the high performance buildings that were compiled from several sources for Montana. And after examining the mechanical systems implemented in these buildings, we came up with a list of high performance systems for Montana that you could see in this slide right here, to the right-hand corner of the slide right here. So as part of this exercise, we also compiled a list of engineering and architectural firms that are currently active in Montana, especially in the design of high performance buildings. So in the next step, we identified a few high performance buildings that would serve as case studies for our report. And in the next few slides, I will be talking a little more about these case studies. So here's the Orange Crush building, and this is a building that was constructed in the 1917 as a grocery store and a warehouse, which later fell into a dilapidated state. So in 2008, a developer purchased this dilapidated building and sought to develop it as a sustainable space with exceptionally efficient systems. So now it serves the Cushing Terrell's Great Falls office. So the building has a number of mechanical systems that are ideal for the type of activities in the building and the climate. So let's start by considering the air distribution systems. The energy code requires ventilated air in the building. So you need to get an outside air into the building. So for that purpose, a transpired solar collector was located on the roof. And this particular piece of equipment is used to capture the heat of the sun that in turn preheats the fresh air intake into the building. So on the other hand, as the outdoor air during the summer is warmer, fresh ventilation air automatically bypasses the transpired solar collector and is directly introduced into the building. So this building also implements demand-controlled ventilation. And this system is paired with the passive solar preheated ventilation air and demand-based ventilation controls. Now, for space heating and cooling, the system relies on geothermal technology to both heat and cool the building with what is known as a warm board radiant product, and only requiring a backup boiler for emergency heat, which is rarely needed. So as part of the central equipment, a water source withdrawal well is used to capture energy from the water underground, which has almost a constant temperature of 53 degrees. So the primary energy source for this building or this water body is the Madison Aquifer that runs under the building. So high efficiency heat pumps that are installed in the building extract this energy from this water and distribute it to the building's custom designed radiant floor system. Space cooling is performed, but without compressors by running the 53-degree water obtained from the aquifer through the radiant flow panels installed throughout the building. And only in some cases, water source heat pumps are used to cool the air where radiant heating is not sufficient or not practical. Finally, we have what is known as the BAS, or the Building Automation System, which is implemented in the building, and that interconnects the solar ducts, the radiant subfloor, the Madison Aquifer, and standard mechanical systems in order to reduce the utility requirements of the building. The BAS also incorporates programming to control the radiant floor system, especially when it's in cooling mode, to prevent humidity issues with the floor as it cools. The next building on our list was the Jabs Hall, and Jabs Hall was constructed in 2015 to house the growing School of Business at the Montana State University. And this building is LEED Gold certified. And the HVAC systems that were selected in this building were not only highly efficient, but also can be considered as experimental. So a little more about the systems, and I did have a video here, which I don't think I should play because I'm scared the system might crash on me. So you can see this on your own time. This talks about how the geothermal system was installed for the building. So let's talk about the mechanical systems in this building. So you do have a closed loop geothermal heat pump that is used to provide heating and cooling for the building. And the pumps move water through the closed loop that reaches 500 feet in depth. And then through a plate and frame heat exchanger, which connects to the building's hydronic system. Now, in addition to supplying heating to VAV terminal units in the building, the hydronic system also serves a radiant floor system that is installed in the lobby of the building. Now, another system that has been implemented in this building is the solar preheated ventilation air system, which is actually a transpired solar collector that allows for preheating of the necessary ventilation air. And depending on the temperature requirements of the building, ventilation is drawn either through the solar collector on the south face of the building, or when the building ventilation system is operating in an economizing mode, the outside air is passed through a louver on the opposite side or the north side of the building, and thus bypasses the solar preheating mechanism. Now, in addition to the supply air, we have two air handlers that occupy a mechanical penthouse located on the top floor of the JABS hall. And one of the units is capable of performing energy recovery through an enthalpy wheel for the cold months of the year, and that is directly connected to the Transpired solar collector. So here's another high-performance building that has been recently constructed on the MSU campus, and this is the Norm Asbjørnsen Innovation Hall, which is a LEED Platinum certified building. And this 110,000 square foot building houses parts of the MSU College of Engineering. And this building has a number of classrooms. It has 7 laboratory spaces and a number of maker spaces, as well as a very large presentation hall called the Inspiration Hall that seats approximately 300 people. Now, the donor's desire for this building was for an innovative HVAC design with a lot of opportunities for mechanical systems to be on display. So there are several features that contribute to the innovative HVAC design at the NAIH. And these include a hybrid ground source heat pump system that also connects to the central steam plant at the university. And this hybrid system allows the steam system to handle cold weather peaks, which in turn allow for a reduced geothermal well capacity. Also, the high efficiency heat pumps in this arrangement utilize the newest variable speed compressor technology. So we also have a natural ventilation system that is utilized as a first stage of cooling in many spaces of the building. And for spaces such as the atrium, the smoke exhaust system doubles up as a natural ventilation assist system. The building also implements a very innovative air quality monitoring system. And the air quality monitoring is used for classrooms, is used for shops and laboratories to modulate the fresh air quantities that are required for these spaces. Now, the system monitors the environmental parameters such as VOC, such as particulates, such as CO2 levels, in addition to the CO levels, in addition to CO2 levels, and adjusts this outside air supply and exhaust levels based on sampling of the indoor contaminant levels as well as the thermal load. So the building also implements a very innovative DOAS that is integrated with other systems in the building. And the system is connected with a heat wheel and the geothermal heat pump to temper in the fresh air that is coming into the building. And in addition, the system utilizes VAV control to modulate the fresh air and the exhaust based on air quality. Now, the system also is connected to an economizer that admits untempered outside air into the building when neither the DOAS or heat pumps are in use. And finally, we have a transpired solar collector that is utilized for outdoor air preheating whenever it is needed. And that too is connected to the DOAS system, and it provides preheated air to the system. Now, other high performance components of the NAIH include a 250 kilowatt photovoltaic array that is located on the roof of the building. And that perhaps is the largest building mounted PV array in Montana. So the final building on our case study list is the High School in Bozeman. And this is another example of a high performance building in Montana. And this particular building was very recently opened in June of 2020. And this school was designed to meet the expanding requirements of the school system in Bozeman. And the school or the building is the first CHIPS certified school in Montana. And for those of you who aren't aware, CHIPS is the Collaborative for High Performance School. It's a certification by which you can start certifying schools to achieve high performance levels. So when looking at the mechanical system of the school, we have an open loop ground source heat pump system that is implemented as part of the central system that provides heating and cooling to the school. And this system takes advantage of the groundwater underneath the ground, underneath the high school as a source of heating and cooling energy. Now, the classroom spaces in the school are served by a VRF system or a variable refrigerant flow system. And that is coupled with this open loop ground source heat pump system. So the advantage of this VRF system is that it allows for simultaneous heating and cooling of different rooms and zones. Also, instead of using air side economizers, water side economizers are now utilized, and water side economizers have an advantage over air side economizers because they are not directly subject to outdoor air conditions, and water economizers can provide longer operating hours and better humidity control. And they also have fewer mechanical components and are less prone to failure. Now, in addition, water-to-water heat pumps are used to provide heating and chilled water to all of the standalone HVAC systems in the building. And these standalone HVAC systems serve gymnasiums, the auditorium, the career education spaces, and the ventilation units in the classroom. Now, these heat pumps too are coupled with the open loop ground source and provide heating water to the hydronic coils that are located in the air handling units for these systems. Now, the heat pumps have a modular design, and this modular design allows the heat pumps to cover the minimum heating loads of unoccupied spaces or modularly increase the production to handle the maximum ventilation loads of these spaces when these spaces are fully occupied. So from the case studies, we selected a number of high performance technologies that we found were a good fit for the conditions in Montana. And here's a short list of the systems, which include HVAC systems, service hot water heating systems, lighting and envelope technologies that were identified for our state. And I'll be talking about each one of these technologies in the next few slides. We also have developed a survey. We developed a survey to assess the potential of these technologies, and you can find the web-based survey at this particular link right here. We have disseminated this survey across the engineering community in Montana, and the results are in the process of being collected and assessed. We, however, have used this survey form to contact a handful of experts to provide us with their opinion on several of these technologies. And although given the small sample size, results are not definitive, but may be considered as indicative of the trends in technology adoption practices for Montana. And using this survey, high performance systems were evaluated for their market readiness, for savings in both terms of dollars and energy, and compatibility with the current utility programs and incentives. Okay. So technologies were also evaluated for their compatibility with the current utility programs and incentives. And here are some incentive programs that are currently being run by the Northwestern Energy. utilities, and these are efficiency programs, and these efficiency programs provide customers with a variety of rebates and incentives to help improve energy efficiency. Now, most Northwestern energy, commercial, industrial, agricultural, electric customers in Montana qualify for these E+ programs. Natural gas customers who buy their natural gas supplies from Northwestern Energy may qualify for custom incentives through the E+ Business Partners Program. Now, so we have the E+ electric rebates for commercial air conditioning, refrigeration, electronics, and appliances. We also can use the E+ electric rebates program for water heating, VSDs, and motor rewind. We also have the E+ commercial lighting rebates that are offered for certain types of LEDs, as well as for certain occupancy sensor installations. Now, in addition, the Northwestern Energy Utilities offers the Business Partners Program, which is more geared towards customized incentives. And to qualify, customers have to demonstrate cost effectiveness of a specific conservation strategy that they have used, or a load management strategy that they have used, or a group of measures that they have implemented in their buildings. And finally, we have incentives for renewable energy installations. And each year, a limited amount of universal systems benefits funding is available through the E+ Renewable Energy Program for renewable energy installations on nonprofit or government public buildings. And these projects and the projects that receive the E+ renewable energy funding must provide civic value that includes education and visible representation of this renewable energy technologies to a broader audience. So this is all the rebates that are available in a nutshell from the Northwestern Energy. And I'm not sure if Whitney or Kramer are here, but if they would like to add anything to it, do raise your hand and let me know.
No, Jaya, I think you did a great job. Thank you.
Okay, that's great. We can move on then. All right. So when considering high performance technologies, let's start with DOAS, or dedicated outdoor air systems. And the primary functions of DOAS is that it uses separate equipment to condition outdoor air that is required by code for ventilation. Now, the advantages of utilizing this system include improved temperature and humidity control, which is much better than if you use a multi-zoned VAV system. It is also associated with reduced energy used because it moves less air around the building. It can be used in conjunction with equipment that does not provide ventilation, like radiant panels or chilled beams, for example. And advanced units or advanced DOAS units can be modulated or improved with technologies such as variable speed fans, such as high performance compressors, and sensors and control logic that could ensure that the unit operates at peak performance. Now, energy recovery options can further implemented or integrated along with this DOAS system can further improve the efficiency of DOAS. Now, applications, when you consider applications of DOAS, it can be implemented in almost any type of commercial or institutional or industrial or even multifamily buildings. And building types with a strict indoor air quality requirements, ventilation requirements, humidity requirements, and energy efficiency requirements can benefit immensely from implementation of this system. So in terms of code readiness and compatibility with the utility programs, the technology is code ready and can be enforced. And it has an overwhelming industry support from the professional and trade organizations. The next system on our list was the variable refrigerant flow system, and these systems have the ability to control the amount of refrigerant flowing to the multiple evaporators in the building. And when installed in different spaces of the building, this type of arrangement provides simultaneous heating and cooling in different zones. And it is known to enhance individualized comfort control as well as save energy. Now, the components of this system include an outdoor unit, which consists of a condensing unit, and an indoor unit, which consists of the evaporators, the refrigerant, and the heat recovery unit. The air source or water source heat pump configuration can be used with this system, like what we saw at the Bozeman High School project. Air source based VRF systems perform best in moderate climates, while water source heat pumps or heat pump based VRF systems are very well suited for harsh climate conditions such as Montana. Now, when considering applications, we have educational facilities, we have office buildings, healthcare facilities, which are best suited. And also historic renovation projects are good candidates as the installation of the systems does not require much space. This system too is code ready and has industry support, and this system has been incentivized by the Northwestern Energy Utilities through, and can be incentivized by the Northwestern Energy Utilities through the Building Partners Program. So chilled beams are the next on our list, and these are fin and tube heat exchangers through which you can either send in chilled water or hot water. And you have different types of chilled beams. You have passive chilled beams that use the buoyancy of the air to that passes over these heat exchangers installed in the space to either cool or heat the air. So you essentially are cooling or heating the space without the use of a fan. Now, in active chilled beam systems, a component of air supply that is passed through the nozzles over the heat exchanger induces the air from the space to get back through the cooling coil or through the heating coil, making the conditioning process much more efficient and effective than what you would see in a passive chilled beam system. Because we need to maintain temperatures of the chilled beam surfaces above dew point, these systems are associated with higher chilled water temperatures, which in turn provide energy savings. Now, when thinking of applications, office buildings, schools, hospital, patient rooms, laboratories, where contaminated air or contamination of air is a big deal and usually is dealt with a dedicated outdoor air system, those are ideal good candidates for this type of systems. These systems are not recommended for buildings which have high latent loads, such as theaters, such as restaurants, such as health clubs. These systems also are code ready, are reasonably well represented in the industry, and can be incentivized by the Business Partners Program sponsored by Northwestern Energy. We also have the geothermal heat pumps, which can either be earth coupled or water source heat pumps. And these have been in use since the late 1940s. So now, instead of using outside air conditions to extract heat, which could have serious implications on both the efficiency and the capacity of the system, especially when operating under cold climate conditions such as Montana, these particular systems use the constant temperature of the earth or of the groundwater as an exchange medium. Now, in an open loop ground source heat pump, groundwater is pumped into the system and passed through a heat pump. And if the building system requires cooling, heat is rejected into the groundwater from the heat pump and vice versa. Now, we found this type of system to be implemented in the Orange Crush building, as well as in the Bozeman High School buildings, where advantage was taken of the water temperature in the aquifers running under the buildings. So these systems rely on the presence of a large accessible water source or a large aquifer under the building, and also require an appropriate location to discharge the water. Now, discharging the water back into the aquifer is the most sustainable of all discharge methods, but may not be permitted by local jurisdictions. Now, this, as I said before, is a system that has been in use since the late 1940s. It is a very mature technology with reasonable industry support and can be incentivized by Northwestern Energy through the Business Partners Program. We also have the closed loop ground source heat pump systems, and these are linked to a closed heat exchanger that is buried into the ground. And we found buildings such as Jabs Hall or the Normus Björnson building greatly benefiting from such arrangements. We also find that most recently manufacturers have developed extended range water source heat pumps for use as ground source heat pumps, and that improves the overall efficiency of these systems. Now, ground source heat pumps or closed loop ground source heat pumps are characterized by high first costs, but low operating costs, high system efficiencies, and these can be, again, considered as mature technologies. And applications could include residential, commercial, industrial applications. These technologies are code ready and have support from the industry and are reasonably well incentivized. We also have a wide spread use of transpired solar collectors in high performance buildings that we considered for our case studies. In fact, 5 newly constructed buildings on the MSU campus have transpired solar collectors implemented. Now, for those of you who are not familiar with this technology consists of this dark perforated metal skin that is mounted on a south facade. And that creates a plenum between the skin and the wall. The skin heats up with the solar radiation from the sun, and the air moves through this plenum space between the skin and the wall and gets heated up. And there are intake ducts that are located at top of the plenum that then suck out the air through that plenum, and then those ducts are connected to the air handling system, which distributes this air into the building. And you can have different technologies and configurations that could be implemented to further heat and to further distribute that heated or preheated air in or around the building. Now, the advantages of this system is that it is very first cost effective. It is reliable, low maintenance. There are no movable parts to that system in itself. And favorable conditions, which include sunny sky or sunny conditions like what we have in Montana, can result up to 40 degrees temperature gain or air temperature gain. And that can significantly decrease the energy required to heat outdoor air. It could be used in either a retrofit configuration or in a new construction, and can also have an excellent and can also be an excellent addition to the heat recovery ventilation system that you have implemented in your building. Jason, you had a question? Jason, you had a question? I can't hear you.
Sorry, that was an accident. I didn't mean to hit that.
Oh, no, that's okay. That's fine. All right. So the potential applications of this particular technology could be commercial buildings, could be industrial buildings, educational buildings that require large amounts of outdoor air. And these, as I said before, are most useful in climates with large amount of solar radiation and very long heating seasons. So when looking at the scorecard, we see that this technology can be code ready and has been and can be incentivized by the Business Partners Program. We also have we also saw a number of radiant heating and cooling systems being implemented in our high performance case study buildings. And these systems provide heating and cooling by use of hydronic elements embedded in ceilings and floors and walls of spaces. So all air systems directly control only the air temperature, but radiant systems with a separate ventilation system control two parameters, air temperatures and mean radiant temperatures. And these systems are far more effective in providing thermal comfort than controlling air temperatures alone. Now, radiant heating and cooling rely on surfaces being exposed in the space to deliver heating and cooling. The energy can either be delivered using radiant panels or radiant slabs. Ceilings or floors are typically used in the installation of these systems, with floors being better for heating and ceilings being better for cooling. And in some cases, coils are embedded into the structure of the building, while in other cases, metal radiant panels are used. And these are particularly suited for retrofit applications. This particular technology is best suited for spaces where steady conditions or steady loads are expected. So wherever you have fluctuation in loads, like for example, if you have solar heat gains from windows, these could be met, these may not be effectively or efficiently met with radiant systems, but you need to install alternative systems to meet those fluctuating loads. Now, while heating and cooling is taken care of by radiant panels, you do need to provide ventilation into these spaces, and ventilation requirements can be provided with independent systems, which in many cases we saw was provided with the DOAS systems. And major limitations of this particular system includes the amount of heating that can be provided by the systems, as well as humidity control. Now, for applications, you can have buildings such as hospitals, schools, data centers are good candidates for installation of these systems. And this particular system is code ready and well received in the industry and is incentivized by our utilities. So our report also considered high performance systems for lighting and building envelopes. And one of the measures for lighting that show promise of deep savings was the luminaire level lighting controls, or LLLC. Now, it's no longer enough to have lighting in a large area to be either on or off. It must adopt two individual needs in response to the changing occupancy, in response to changing daylighting levels, in response to the desired lighting levels required by the occupants to conduct different activities in the space. Now, LLLC strategy incorporates this complete set of sensors into each luminaire. So now each luminaire is autonomously controlled as a unit. And this level of granularity and control can result in up to 50 to 80% of savings in lighting energy. So LLLC systems can also be implemented with wireless controls to communicate with other luminaires in the space, and can be controlled on a systems level. So you can control this LLLC on a luminaire level, but you can also control it on a systems level. And the installation of this wireless controls technology is as easy as installing the luminaire. And once the system is installed, it's easy to operate using a smartphone app. So this technology also plays well into the fact that commissioning of lighting systems, although recommended by the code, has never been really taken up seriously in the past. And the simple interface of control technology can actually help in enforcing commissioning of lighting systems. Now, the system is currently being specified in the code in the 2018 IECC. It does have a rising industry support and has been incentivized by our utility programs. So dynamic lighting is one other feature that we considered, or a strategy that we considered. And this refers to lighting system that is programmed to fluctuate in color temperature. Now, I'm sure you're aware of color temperatures of different lighting systems in your spaces. Some are cool color temperatures, like those associated with fluorescent lamps, and there are warm color temperatures that are traditionally associated with incandescent lamps. So a dynamic lighting system can actually be programmed to fluctuate the color temperatures as well as the illuminance levels while adjusting to the varying color temperatures of natural daylighting. Now, the characteristics of this particular dynamic lighting system is that the use of LEDs and lighting sensors technologies that actually can increase the energy efficiency. This particular system can be calibrated based on the task required and can be very effective in a windowless environment because they can promote circadian rhythms to improve the productivity and occupant comfort of the people in the space. Now, applications of this particular system include elementary schools, offices, industrial settings, which are typically associated with windowless environments. Now, while this is code ready and it does have certain a level of industry support, this particular system may not really show you much of energy savings, although it can show you much in terms of improved productivity of occupant comfort and in terms of, it can show you a lot of benefits in terms of occupant productivity and occupant comfort. We also have seen the use of dynamic windows in some high-performance buildings, and dynamic windows involve changes to the characteristics of windows, including SHGC or visible transmittance. And this change in characteristics depends on the triggers from external environment, such as exterior lighting levels or solar radiation incident on the window, or electric signals that can be user controlled. Now, these technologies can be applied to all types of commercial buildings. And while these technologies are referred or referenced in the IECC commercial codes, they do not have good support in the industry in terms of sourcing and are usually very high, usually are very, very expensive to install. So one type of PV cells that can be integrated in the building envelope is referred to as building integrated photovoltaics, or BIPV. Now these technologies, these are technologies that can replace the building envelope. They are really technologies that are not put on top of the envelope, but they actually replace the building envelope itself. Now, BIPV is the envelope itself, and BIPV in the envelope has to meet building codes. Now, there are European standards that exist for BIPV, but standards are being developed in the United States and Canada. Now, when it comes to BIPV performance, we actually have to account not only for electricity generated by the BIPV, but also the hygrothermal performance, the daylighting performance, and the heat recovery performance of the building envelope component. So not only does this technology impact the engineering decisions, but also impacts architectural decisions that we make in our buildings. And that calls for an integrated design process that we have to utilize in our buildings. Now, both opaque and thin film technologies are available. And applications would include commercial buildings, would include retrofit situations, would include skylights and greenhouses. This is code ready. This has industry support, and because it is a renewable energy technology, it can be incentivized by the E+ Renewable Energy Program. So here are some conclusions that we came up with based on the interviews and surveys that we conducted thus far with the experts. So now when considering energy saving opportunities, cost effectiveness, and measurability for HVAC technologies, we have closed loop and open loop ground source heat pumps as well as VRF technologies. These technologies demonstrate medium to high energy savings, and these technologies were marginally cost effective. The savings from the implementation and operation of these technologies were readily quantifiable. Also, on one hand, ground source heat pump systems were characterized with minimal maintenance, while on the other hand, VRF systems required substantial involvement from the O&M staff. We also found that technologies such as chilled beams, transpired solar collectors, and radiant heating and cooling technologies do have a low to medium energy saving potentials. These are marginally cost effective, and the savings are also quantifiable with detailed measurements and evaluation data being readily available. When considering technologies being defined, available, and market-ready and market-friendly, VRF and DOAS systems are available from numerous manufacturers. When considering ground source heat pumps, the heat pump equipment for these systems are available from numerous manufacturers, but the installation of ground or water heat exchangers on site are very site-specific and require customization. These technologies are ready for both design and construction market. Implementation of these technologies was associated with medium to high costs. These technologies do meet code requirements and are associated with some non-energy benefits such as improved thermal comfort, improved indoor air quality, and reduced noise levels. When considering technologies being defined, available, market-ready, and market-friendly, both radiant heating and cooling technologies as well as chill beam technologies are mature technologies. They are available in the market at least from 3 sources. These technologies are design and construction ready. All these technologies have lower costs than all air HVAC due to the elimination of ductwork, and there are significant non-energy benefit related benefits such as improved indoor air quality and thermal comfort of occupants related to these technologies. However, additional dedicated ventilation systems have to be provided. And finally, these are widely accepted in cold, dry climates of Montana, as humidity control is not of a big concern. And finally, when considering program support in terms of code readiness, in terms of industry support, compatibility with utility programs, and incentives provided by the utility programs, all technologies can be implemented on a voluntary basis. Industry support for these technologies can be considered supportive. At best, most of these technologies are currently being incentivized by various utilities programs. So for high performance envelope and lighting technologies, when considering energy savings, we see that dynamic lighting, LLLC, and BIPV technologies do provide sound cost effectiveness and measurability. BIPV provides high energy saving opportunities. There are no unitized energy savings currently available for dynamic lighting because it's more associated with human comfort and productivity rather than energy savings. And we also have found that dynamic window technologies are not associated with high energy saving opportunities, cost effectiveness, and measurability. When considering market potential, dynamic lighting and LLLC technologies are currently being available from different vendors. These technologies are associated with high costs or high first costs. However, there are numerous non-energy benefits, non-energy related benefits, especially for dynamic lighting, such as enhanced circadian rhythm, associated with the implementation of this technology. Dynamic window technologies, on the other hand, are available through unique sourcing. These technologies are in the nascent stage of their commercialization and also are associated with high costs. And these technologies, especially in commercial settings, have few non-energy benefits and are really not market friendly. And when considering compatibility with code and utility programs, once again, all technologies can be implemented in voluntary situations, do have some form of industry support, and except LLLC, all other technologies are currently not, can be incentivized, but yeah, so are not really highly incentivized. And finally, here are some outreach materials published by NIA, and these tech sheets provide some basic information about high-performance systems that are viable in Montana, along with the case studies that demonstrate their effective performance. Now, here's a tech sheet for ground source heat pumps, and you can find this and other tech sheets on the Better Bricks website. The presentation, this particular presentation will be available on the NCAT website, and this is my email out here. And do you have any questions for me before we go on a 5-minute break? Any questions? All right, I guess we can go for a 5-minute break right now. Thank you so much for your attention. My next presentation will be on lighting technologies that can be adopted in the code. Thank you. Moore, who is the founder of Beartooth Lighting Consulting, who helped us in compiling and reviewing this presentation. So here's the overview of this presentation. I will be talking about the requirements for lighting of in the 2018 IECC. Not so much as what is there in the code, but what has changed from the 2012 IECC. I will be then providing an overview of the lighting technologies and controls that can currently be implemented to meet the requirements of the 2018 IECC. And in this section, I'll be providing an overview of the conventional technologies, as well as providing an overview of the new technologies that are out there to meet the requirements in the code. Then I will be touching upon incentives and barriers to implementing new technologies. I will be looking at certain incentive programs offered in Montana, some of which are sponsored by the Northwestern Energy. And finally, I will be presenting some case studies of buildings that have implemented high-performance lighting technologies. So in this section, I will be highlighting the changes in the lighting section of the 2018 IECC. So one of the biggest changes that we see in the code for lighting is the reduction in lighting power allowances. And this reduction addresses the advances made in the lighting technologies with the arrival and advancement of LEDs in the last couple of years. We also have changes in the equations for calculating the interior lighting power allowance for retail and sales areas, with smaller areas now being allowed additional lighting power and larger retail sales areas having restricted lighting power usage. Now, additional lighting requirements that is typically provided for decorative purposes have become more stringent. Now, additional lighting power in lobbies must not exceed 0.9 watts per square foot, and additional power, lighting power in for other spaces can't exceed 0.75 watts per square foot. Requirements for exterior lighting power densities have changed too. And some of the highlights include a reduction in lighting power allowances for building exteriors, and a snapshot of which is provided in this table right here on the slide. Also, tradable allowances for lighting power have been removed. And there has been an inclusion of categories such as loading docks, exterior dining areas, landscaping in the requirements for these allowances. And finally, exceptions to these power allowances no longer include historic buildings. So the code now specifies LLLC in their own category, and these systems must be independently capable of monitoring activity as well as ambient space lighting conditions, and accordingly brighten and dim lighting outputs of the luminaire. The system should also allow for the configuration and reconfiguration of control strategies associated with the luminaire. And these control strategies include dimming set points, timeouts, fade rates, sensor sensitivities, and wireless zoning controls. We also see more stringent requirements for interior lighting controls. Occupancy sensors are now required for different sizes of open plan offices, with more stringent requirements for turning off the lighting systems when not in use. And we also see a requirement for time switches in areas without occupancy sensors or light reducing manual controls. Now, requirements for daylighting have been modified, and integration with daylighting is not required now if it can be demonstrated that lighting power allowance is less than or equal to the adjusted lighting power allowance as calculated in this equation presented in this slide. We also see more stringent requirements for exterior lighting controls, and lighting controls are now required to automatically shut off the lighting between midnight and whenever the facility opens. And a list of shut-off strategies include daylighting shut-off, exterior occupancy controls, exterior dimming, as well as time switch controls. And finally, commissioning of lighting that has been introduced, was introduced in 2015 code, and specifications for commissioning of lighting systems are now mandatory. Now, requirements include testing the functionality of automated control sensors such as occupancy sensors, time switch controls, and daylight responsive controls, and the requirement for documentation, which include provision of drawings that indicate the location and an inventory of lighting fixtures in the facility, manuals of O&M of lighting, for O&M of lighting systems, and a report that provides results of the functional performance tests that were performed on lighting controls, and the measures the owners can take to improve deficiencies, if any. In the next section, I will be presenting a short discussion on lighting technologies that are currently being implemented. And this includes legacy lighting and current lighting technologies. And current lighting technologies will include a discussion on LEDs, replacement possibilities, and applications. We have a number of lamp types which have been listed as legacy lighting technologies. And these lamps are still used for maintenance purposes, but are not being specified as part of new construction. Now, the first type is resistive technologies that essentially operates by heating an element. Now, in resistive technologies, we have incandescent, which in the past has commonly been used in residential buildings, but more recently this technology is being replaced by LEDs. And many such bulbs have been phased out from production starting in 2014. Now, another variation of resistive technology is the halogen lamp. And halogen incandescent is an incandescent lamp with halogen gases. Now, it's more efficient light source than the traditional incandescent, has higher light output than an incandescent, and is still used in certain residential and commercial applications, as well as in spotlights, and is available in a variety of color temperatures. We also have another type of legacy lamp known as the discharge lamp. And these essentially work on the principle of sending an electric discharge through an ionized gas in order to generate light. Now, examples of such technologies include fluorescent, include metal halide, include sodium and mercury lamps. For fluorescent, we have both tubular lamps as well as compact or curly versions of it. Some years back, CFLs or compact fluorescent lamps were a common replacement for incandescent lamps in residential buildings. However, these days, CFLs have been completely replaced by LED lamps. We also have tubular fluorescent fixtures that are still used and specified. And linear standards include 2 feet, 4 feet, 8 feet long tubes. We also have T8s, T5s, and T5HOs that are still being used. And HO stands for high output, meaning that these lamps deliver more light than the standard T5 lamp. And these, once again, are available in variety of color temperatures. Now, metal halide and sodium lamps are primarily used to provide most light with least amount of wattage. And the applications of these lamps include arenas, street lights, gyms. And finally, we have what are known as mercury vapor lamps, and these are more efficient than incandescent lamps. However, they have a very poor color rendering that is not really flattering to the human skin. And these have been used in the past in factories, in warehouses, in sports arenas, as well as in street lights. The current lighting technology of choice has been currently overrun by solid state technology. So the markets right now are totally being overrun by solid state technology. And this technology utilizes semiconductors to convert electricity to light. And solid state lighting applications include LEDs, OLEDs, and electroluminescence. Now, LEDs stand for light emitting diodes, and these are semiconductors that produce light. And the light color is determined by this chemical coating of semiconductors, with white light being achieved by blue LEDs with phosphorus coating. And these lamps are associated with high efficacies, almost up to 150 lumens per watt, which is actually comparable to daylighting. And they also have a very long lamp life, which makes them suitable for a wide range of commercial applications. Now, OLEDs stand for organic LEDs, and these are light emitting panels that are made from organic based materials that emit light when electricity is applied. And unfortunately, the high price of production can be a challenge to incorporating these technologies into buildings. But they do have a niche market that includes automotive markets, that includes health markets, and that also includes premium designer markets. Now, finally, we have what are known as electroluminescent technologies, and these have been around since the 1960s. And this particular technology consists of phosphorus layers sandwiched between two conductive layers. Now, very minimal energy input is required to emit light, and these technologies can actually operate from being exposed to electric light or daylight. And these are typically used in exit signs or decorative applications, but should be discouraged from being used for exit signs because they have liability issues involved with them, with their applications. Now, here are some characteristics of LED lighting technologies. With these technologies, both static white and dynamic white light products are available. We also have what are known as selectable products. In other words, you can set the lighting color temperatures of the luminaires after taking them out from the box or changing the color temperatures of the lamp with the flip of a switch. So also these technologies have the potential to be fully dimmable, and the products using these technologies are available for almost all application types. Now, LEDs offer a huge variety of benefits, and some of the advantages of utilizing LEDs are that they are associated with very high efficacies, with efficacies over 100 lumens or over 150 lumens per watt. The efficiency or the efficacy of lights, these LEDs can be comparable to daylight sources. And also LEDs are a directional source of light, which means that efficient optics is possible with this technology. We also have LEDs that are associated, these particular lighting systems or technologies is associated with high CRIs as well as a range of color temperatures, and also performing well with the new system of assessing color rendering capabilities, the TM30. So the LEDs are also characterized with a very long lifetime of around 100,000 hours. And although the performance of LEDs does degrade over time with factors such as temperature, voltage, playing an important role in the degradation process. So while there are minuscule traces of mercury and lead in these products or in the products of this technology, in many cases, there have been steps that have been taken to replace the lead solders with lead-free materials. We also have other advantages of LEDs, and the energy emitted by LED sources is in the light spectrum. Versus other lamps such as incandescent that emit energy both in the light spectrum as well as in the infrared section of the electromagnetic spectrum, hence emitting both light and heat. We also can utilize LEDs for cold operation, meaning that LEDs can easily be operated under very cold conditions or under very cold temperatures and conditions. Also, LEDs by nature of their construction are resistant to impact and vibration, as opposed to, say, gas-filled lamps such as fluorescent or sodium lamps and filament-based lamps. And this allows LED technologies to be used in industrial setting, where we are concerned about vibrations from machinery affecting the lighting systems installed in those buildings. The technology also allows for rapid switching, even when operating under cold conditions. And this ability to switch to control the LEDs on and off rapidly under such conditions makes them an ideal application for refrigerated cases and refrigerated boxes. Here's some more information about the usefulness of LED lamps, and the rated life for conventional lamps is very well established. The lamp life for a conventional or the lamp life definition for traditional light sources is the time at which 50% of the test samples have burnt out. On the other hand, LEDs generally do not fail by burning out, but will slowly reduce in light output over time. And hence, these technologies are rated in terms of length of time a source delivers a minimum acceptable level of light in a given application. So in other words, the life of an LED fixture is measured in terms of lumen maintenance, or LP, where L is the initial output and P is the percent of lumens maintained over a number of hours. So for example, an LED with a rating L90/60,000 means that when tested, 90% of the initial lumen output is reached in 60,000 hours. Okay, so that's what an LED with a rating of L90/60,000 stands for. So LEDs are currently replacing a wide variety of incandescent and halogen screw-based lamps, as well as fluorescent T12s and T8 lamps. Now, LED bulbs now can be used in place of common incandescent bulbs, and recent improvements in LEDs have surpassed CFL performance. Also, screw-based directional LED replacement bulbs fit into the same medium-based sockets as common incandescent reflector bulbs. Linear fluorescent lamps can be replaced with LEDs. The target is T5, T8, and T12 lamps or T12 tubes. Pretty much the same advantages and disadvantages as I mentioned in my earlier slides. We have advantages that include energy savings, maintenance savings, no mercury or lead, cold starting, shock and vibration resistant, while disadvantages could include poor lighting output. Replacement LEDs may need to add lamps to maintain the adequate lighting levels, and also a strong directionality, which may be a problem in general lighting, if not adequately addressed by the luminaire or by the fixture or by the housing of the luminaire itself. So these retrofits are either done with a type A or type B LED fixtures, and sometimes referred to as plug and play. You have type A LED lamps that directly replace the traditional types such as compact fluorescent lamps or linear fluorescent lamps. And there is no rewiring that is required, no electrician that is required. You can simply replace your existing lamps with a new type A LED lamp. However, a type A LED are not compatible with all electric or all existing ballasts. Now, type B, on the other hand, requires rewiring for the fixture to supply line voltage directly to the lamp holder or sockets. So in other words, you do not require a ballast for type B replacements. So the following slides present snapshots of the applications, and LED outputs can now be designed to achieve batwing distribution characteristics of light output from the lamp. And these characteristics are very valuable in classroom scenarios and in office applications. You can also use LEDs to create sculptural lighting installations and taking advantage of flexibility and of the flexible form factors associated with this technology. Directionality can be utilized effectively in track lighting. Like what you see out here, we have track lighting installed in this particular scenario. And LEDs are best suited for track lighting situations. And most recently, LEDs have made a major surge in office lighting with technologies exhibiting high CRIs and a wide range of CCTs, as well as a very long life. Cold start and instant start capabilities have made LEDs ideal for lighting refrigerated cases. And now you can also add dimming capabilities to such lighting technologies to further save energy in grocery stores. And also resistance to impact and vibration has made this technology very appealing to industrial applications as well as hazardous areas applications. So in the next section, we'll be looking at lighting controls that are currently being implemented in the building and comply with the energy code. But first, let's look at why we need lighting controls and why the code is paying more and more attention to incorporate lighting controls in its specifications. So the first thing we have on our list is flexibility. And with flexibility, one can change luminance as well as lighting patterns in a space on implementing lighting controls. Now, lighting controls also are associated with savings in terms of energy and monetary resources. So a reduction in 60% energy usage was reported on utilizing more advanced lighting controls over on-off control systems. We also see an increase in bulb and ballast life on implementing lighting controls. And finally, implementation of lighting controls are also associated with reduced cooling loads that result in lower air conditioning loads and costs. We also find, we also have improved productivity and user satisfaction associated with controls. And as these systems are utilized to provide different appropriate lighting levels for different tasks, we find that more occupants or more people are comfortable or satisfied in the spaces that have these different lighting controls implemented in them. As well as reduced maintenance costs, as the implementation of these systems is associated with increased lamp life, as well as reduced stocking space. So here are some typical and state-of-the-art lighting control technologies. Now, typical lighting control strategies include manual switching, include dimming, scene controls, timer controls, daylight integrated controls, and occupancy and vacancy sensors, while the latest lighting control strategies include manual switching, dimming, scene controls, timer controls, daylight integrated controls, as well as, color temperatures, dusk tuning, and luminaire level lighting controls. So let's look at the different control functions in a little more detail here. So the first control function is the switching or manual switching, which is an on-off function, and it is relatively simple and inexpensive. It does have limited flexibility and is not the best of energy conservation tactics. However, occupants have full control over the conditions they want to create in the space. Now, designer can achieve, or the designer can select multiple switching levels, either by turning entire luminaires or portions of luminaire off or on through these on-off functions and controls. Okay. We also have dimming, and the reason why we dim light sources is additional energy savings as well as enhanced space flexibility. And with dimming systems, we need fewer light sources to specify, to maintain, and to stock. And these systems are more expensive than manual switches, but they do have increased flexibility over manual switching controls. Now, the cost of dimming hardware is high for fluorescents because of the additional cost of dimming ballasts, and low for LEDs because often these lighting systems come with integrated ballasts. Now, dimming essentially involves reducing the lumen output by reducing the power input, and not all lamps perform the same way. As you can see out here in this graph, not all lamps perform the same way. So lumen output as a function of power input for generic lighting sources is very different for different types of fixtures. Now, fluorescents are the most efficient till 40% of their power input, while other sources demonstrate reduced efficacy when subject to dimming. Okay. So also important to note is the wide variation in LED sources and dimmer characteristics that lead to a wide variation in dimming performance and compatibility of LED systems. We also have scene controls, and sometimes it's easy to meet the requirements of the space with certain pre-established set of lighting. And with scene controls, certain pre-established luminance levels and illuminance distributions can be established. Now, user interface is easy with the user selecting a preset lighting control by just pressing a single button. When using scene controls, fade rates have to be accounted for. Like for conference rooms, you can have relatively fast fade rates, while on the other hand, for restaurants, you need to have relatively slow fade rates to make sure your occupants are comfortable. It should also be noted that while on one hand, these controls are associated with added costs, on the other hand, these controls greatly simplify user interaction with controls in order to attain the established lighting levels. We also have time controls or time-based switches, and these are useful in spaces that have consistent operating schedules and that can either be mechanically or electronically controlled. And example of mechanically controlled time switches are contacts. Contacts are made when the example right here is an example of a mechanically controlled time switch. So now contacts are made when the knob is rotated and the circuit breaks at the end of the timed cycle. So another variation of time controls is the astronomical time clock, and that is used mostly in exterior settings where lights are turned on and off based on the sunrise and sunset patterns. Now, when using these controls, we do need to have manual override capabilities, and in the event of the space being occupied outside normal occupied hours. We also have to have a combination of sensor and timer controls, and the sensor will direct the lighting system to turn on and can be either a photo sensor or an occupancy sensor. And then we need to have a timer control to turn the lighting system off. So another control strategy is daylight responsive control. And daylight responsive control, also known as daylight harvesting, uses a light sensor that also is called a photosensor or a photocell with a power controller to switch or dim the lighting in response to available daylighting. So as the light levels rise above a target threshold due to daylighting contribution, the photosensor signals the controller to reduce the light output and thereby saving energy. So the response to these sensors can either be by switching or dimming, with switching being undesired because you have these switched on and off light levels that can disturb occupants while they're working in a space. And automatic or automated dimming is preferred over switching because it has a gradual dimming effect on the light system in the space, thus contributing less to the occupant discomfort. So when implementing dimming, appropriate fade rates and dead bands must be considered. So you do need to think about dead bands, because a dead band is actually a tolerance of the sensor for detecting daylight changes and adjusting the lights. And this is so that the short changes in daylighting do not continuously trigger light adjustments and hence cause occupant discomfort. So now when installing daylighting sensors, establishing zones is extremely critical, and a south orientation is a good candidate for daylight sensors because of the high fluctuation of daylight in that space adjacent to the south orientation. In addition, latitudes needs to be accounted for because in higher latitudes, we have low winter sun that can penetrate the space to a greater degree, and that requires a second zone of daylighting control. We also have occupancy sensor controls, and these are devices that are automatically turn the lights on or off based on whether the space is occupied. These have motion sensors that detect occupancy and direct lights to be either turned on or off, depending on how the sensor is being configured. Now, essentially, there are two types of sensors. We have occupancy sensors that turn the light on and off in presence of occupants, and you have vacancy sensors that requires the light to be manually turned on and turn off the light in the absence of movement or in the absence of occupants. Now, a common control strategy that is used along with occupancy sensors is the return to dim level. And that, in other words, means that when activated, the lights return to a dimming level set by the occupants before leaving the space. Now, private offices typically are unoccupied 30 to 60% of the time, and can greatly benefit from the installation of these sensors. And these sensor technologies can also be configured with other devices and can also be used to control other devices such as fan coils, such as air conditioners, such as fans. Now, you have different types of occupancy sensors, and these include PIRs, which are passive infrared sensors that detect major movements. You have ultrasonic sensors that detect finer movements, and then you can have dual technologies that utilize both these technologies and that work in tandem to detect occupancy of a space. Also called institutional tuning or high-end trim, task tuning allows for light output levels to be adjusted to the applicable task in space. This could be done either in the commissioning stage or when installing and testing the luminaire or over a lifetime of the luminaire. So as adoption of dimmable lighting grows, task tuning is becoming now an increasingly viable as a way to save energy while increasing occupant comfort. And you have dimming lighting or dimmable lighting can still be controlled as usual to implement other strategies such as manual control and daylighting harvesting. However, with task tuning, the high-end light output level is capped, and that results in permanent savings through dimming. You can also have color tuning, which is the ability of luminaires to change the color temperature of the light output. And this particular control strategy is primarily applicable to LED fixtures. Now, LED luminaires with the ability to deliver varying light color have been on the architectural lighting scene since the early days of LED lighting. But improved efficacy, improved color controls, improved controls and capabilities have expanded this range of potential applications. Now, by dimming different arrays of LEDs, you can adjust the color temperatures of the light output. And you can do this to accommodate for different usages that have been designated for the space. In other cases, the dynamic lighting system can automatically adjust the color temperature to produce idealized daylighting conditions in that space. And this particular variation of the dynamic lighting control strategy plays an important role in regulating what is known as the circadian rhythm of the human body, thus increasing productivity of occupants in that space. We also are seeing more and more of wireless technologies that are being used to install, set up, and monitor lighting systems. And these control strategies can be used for all types of lighting control scenarios. And the advantages of wireless control systems include flexibility, include ease of integration with the building automation system installed in the building, the ease of access from any computer or any mobile device, simplified installation, simplified setup, simplified commissioning, as well as very convenient maintenance. On the other hand, you do have some disadvantages that are associated with wireless controls. And these include that in many cases, you do need requirements for battery replacement. And also sometimes software requirements or updates of centralized systems don't always go in lockstep with the systems or with the software that has been installed to regulate your wireless controls. Finally, we have what is known as the luminaire level lighting control. And as energy codes and energy efficiency goals become more and more demanding, there is a need to maximize energy savings from commercial lighting systems. So, rather than a conventional approach where lighting control zones are defined and controlled as a unit, the LLLC strategy now incorporates a complete set of sensors into each luminaire. And this fine granularity of control associated with this LLLC technology can provide significant savings. So here is an example of the different type of sensors that can be used in a private office space scenario. And in this type of space, personal control of light is very important. And research studies have found that occupants are more productive when they can tailor lighting levels and qualities and lighting qualities to their current requirements or to their current needs. Now, this particular example has several solutions, which includes a wireless switch that provides manual control, as well as switches lighting loads in response to the wireless sensors and controls. It also has a ceiling mounted occupancy vacancy sensors that communicates with the load controllers to turn the lights on and off based on occupancy. And it has a daylight sensor that communicates with the load controllers to turn the lights on and off based on the amount of daylighting that is available. So utilizing these sensors or this set of sensors can provide lighting energy savings up to 50%. And the return on investment has been calculated to be approximately 3 years. Now, here is another example, lighting for classrooms. And lighting for classrooms is important for quality of light and lack of distractions to enhance the learning environment for students. And research has shown that there is a direct correlation between good lighting levels in a classroom and high student performance. Now, daylight integration and dimming systems can save energy, but fade rates have to be carefully specified not to disrupt the students or not to distract the students with the different light levels, with changing the different light levels in the space. Now, manual controls can override the system to provide scene controls in the classrooms, and controls communicate through power packs to dim lights. Now, this particular example has several solutions, which includes a dimming module, right here that responds to the wireless sensors and controls, and in turn controls the lighting system. This includes a digital ballast right here. This includes a daylighting sensor that communicates with the load controllers to turn the lights on and off based on the amount of daylighting available. And this particular scenario, utilizing these sensors, can provide lighting energy savings of up to 77% with a return of investment of approximately 2 years. So implementation of high performance lighting controls can be incentivized. And here are some incentives that you may take advantage of when implementing high performance systems in your buildings in Montana. And some of them are sponsored by Northwestern Energy. Finally, I'll go over a number of case studies that have been implemented, advanced lighting control systems and controls. In this first case study, we have the use of LED systems in a grocery store to light up cosmetics shelving units. And the directionality of the LED was manipulated to direct the lighting level on the shelves, in order to achieve the desired vertical illuminance levels that are required to light shelves in grocery stores. And to eliminate, this particular technology eliminated the need of 4 kilowatts of under-shelf lighting that is typically associated with the display of cosmetics in stores. Also, the lighting power density of this grocery store was 0.89 watts per square foot as compared to 1.4 watts per square foot, which was required by ASHRAE standard 90.1 2010. Here's another case study, and this showcases the use of LLLC technology at Pacific Tower, which is located in Seattle, Washington. And the implementation of the LLLC system added additional savings on top of LED retrofits, and 80% of energy savings than originally, 80% energy savings were established and originally expected from this new system. And this type of system proved to be ideal for the Pacific Tower, which has a variety of tenant types and occupant uses, with each tenant being able to get the right lighting for their requirements. And also wireless controls associated with the system allows the system to be recommissioned without changing out any of the hardware or infrastructure. And here is another case study of the Puget Sound office renovation in Bothell, Washington. And the original light system was delivered by a 32-watt T8 fixtures, and this resulted in low and inconsistent lighting levels due to lighting layout of the system. And 67 of the fixtures in the original system were then replaced by 100 LED fixtures with LLLCs, or luminaire level lighting controls. And retrofitting the system with LED lamps alone provided 34% energy savings, while incorporated the integrated lighting controls provided 72% of energy savings when compared to the performance of the base case lighting system. So also the owners commented that the installation was quick and easy due to wireless controls, and the occupants enjoy this increased lighting comfort from the lighting levels and dimming capabilities of the new system. With that, I complete my presentation on lighting, and I will take any questions if there are. No? All right, well, thank you very much. And we will be going on a 15-minute break. Thank you so much.
Well, I think everyone is probably ready, so I'll go ahead and get started. My name is Kevin Amendi. I am an associate professor of mechanical engineering technology at Montana State University, and I co-direct the integrated design lab with Jaya. And so this is a presentation that I had a student work on this past year that kind of covers a topic called unglazed transpired solar collectors. And so Nick Haug couldn't be with us today. He was originally scheduled to present face-to-face and was super excited about it, but he graduated and is now in Wyoming working and being gainfully employed. So that's a great thing. So I'll give a little bit of background on some of the solar energy collection that we typically see out there in industry right now. And photovoltaic panels, everyone is pretty aware of photovoltaic or PV panels and their applications in the built environment. So we're seeing those mounted both on rooftops, but we also see a lot of land mounted applications as well. We see more utility companies putting out solar farms in that regard as an option. And then on the other two fronts, we have passive and active solar thermal. So our PV panels, obviously, they take use light protons and transfer that energy to be able to create a DC voltage that then we convert into AC and put to the grid system or into battery banks that could be run in local areas. It's currently estimated, based on our sources, that in Montana, cost per watt is approximately about $2.95 in our area. And we know that also as manufacturing techniques improve, efficiencies of different technologies happen, PV prices have actually dropped somewhere around 20% over the last 5 years. So it makes it more economical to utilize systems like that. And then there are also incentives out there that can reimburse the installation costs of these systems as well. And some utilities will have a specific cost for just the panels themselves or a rebate system for that. Some will go through and actually incorporate installation costs with that too. So we see that even in the geothermal installation world now, where some of the installation costs, depending on the utilities, will actually give credit for those situations. Here's just an example of an installation of basically ground mount installation of PV panels. These are easier access. So one of the big challenges as architects, I guess one of your biggest challenges is if you're designing buildings that are going to incorporate PVs on rooftops, you're going to run into the issues of having to make sure that there's additional structural members and supports. There's going to be more penetrations through any roof membranes that are out there. And then there has to be appropriate setbacks from any of the exterior walls and stuff. So from life safety standards, you got to be able to do that as well. And then sun angle, so location. So you can see that these photovoltaic panels are pretty much vertical. They have a very shallow incline to them. Well, it's very steep, I guess. Shallow or steep, depends on what your norm is. In this process, it's to make sure that when they are operating in a ski area, it's happening in the winter and you have low sun angles. So they are looking at the operation and maximizing the energy produced by those PV panels during the season that they're actually occupying the buildings and utilizing the energy. And so that's not the typical angle that we see in Montana for fixed panel orientations for most facilities. So if these were on top of a building, at that angle, we wouldn't be able to put very many panels on there because panels closest to the south side would actually be shading panels just behind them to the north as the sun transitions from east to west in those situations. So when we look at passive solar thermal, I think all architects are very well versed in this. It's one of the fundamental designs, I'd say, for when buildings are oriented, when you're looking at overhangs or other shading devices. So from a passive strategy, it's great to be able to do this. I'm in the mechanical engineering realm where we typically, we can brute force anything if we have to, right? We can activate systems, but we do want to minimize how much we have to run heating or cooling systems. And so in this, by having good south-facing walls, maximizing your solar gain and shading potential on those. Dark materials is another way of either absorbing energy if we're looking at it from the heating standpoint, or obviously we see a lot of white membrane roofs and light colored buildings in locations that maybe have a lot of sunshine year-round, where they primarily need to be cooling in those, and so they're trying to not absorb that. So we can look at different strategies for that. And then obviously this is going to affect all three modes of heat transfer for us. So natural convection, conduction, radiation. So when we're absorbing that material, we can absorb radiant energy, and that can be stored in different thermal masses or building constructions. When we look at this from the convection standpoint, when those surfaces start warming up, we start getting drafts. So a lot of people will experience this in the middle of winter, where you could have a fixed panel, a non-operable window, but it feels like there's a draft right next to that window all the time because it is pretty cold outside, and you're getting a temperature difference that's really close there, and it's basically causing a draft effect, drawing in some of the warmer air as cold air sinks next to that window and is being cooled off through the temperature change through that. So you can see some of those things. This would be a typical image of what that would look like from our passive solar thermal. So we don't have to activate any systems. Winter sun at those low sun angles comes in through our south facades, and our glazings in that process. In the summer, when we don't want it to be absorbing any additional energy, we have well-designed roof overhangs and or other shading devices to be able to eliminate that. So hopefully you're not hearing a helicopter in the background, but sounds like there must be something going on outside. Active solar thermal. So this really is an area that we've had a lot of solar thermal collection throughout the years, but we can break this down into a couple different realms. We have solar concentrators. So we see this in a lot of different solar thermal hot water heating systems. And then we also have the ability to look at regular solar thermal ones from the heating of air or the water primary system. The one that I'm going to go into a little bit more detail about today is our UTSC, or our unglazed transpired solar collectors. These would fall into the realm of heating air. And so these are preheaters for building DOAS systems or other air handling systems, but anytime you're bringing in your dedicated outdoor air, we have certain minimum requirements for pulling that air into our buildings. And with the current situation with COVID and having other areas, we need to increase our outdoor air percentages to help get better quality air into those facilities. And so these actually are a great strategy for this in locations in the northern part of the United States and in Canada. So any area that basically still could see plenty of sun, but is a primarily heating dominated from an HVAC standpoint climate, you want to go through and make sure that you want to minimize the amount of energy or fresh air coming into the building that you would have to heat. So there is a little bit of a blur between solar concentration and solar thermal. So if we look at solar concentration, both at like a utility and a domestic scale, domestic type applications here could be hot water heating. And so we could have vacuum tubes, hot water heating devices to be able to increase those in domestic or small commercial applications. We see a trend when we were starting to look at prices per watt of cost of photovoltaic panels and generation there. As those become cheaper and cheaper, they have hit a threshold in certain areas, especially depending on rebates, where if you have domestic hot water production that you're looking at doing, and maybe you would have originally put in a solar thermal panel system, it may be cheaper now to run a photovoltaic system and use that energy generated from the PV panels to actually use electric resistive heating in the hot water heating tanks for that. If we look at the utility side of things, this is where you see a lot of work taking place in California, Arizona, and New Mexico. I've seen some of these facilities in Arizona that are used basically to superheat the air to produce or concentrate that air to be able to produce hot water that then can actually boil and turn into steam. And then they use that steam for turning turbines to generate, and then they can output that directly onto the grid. So hot water collectors. Basically, we're using concentrators or reflective mirrors to be able to go through and do that. And so this is another process that is out there and available on the concentration side. So if we start looking at unglazed transpired solar collectors a little bit more closely, there's been plenty of work done down at the National Renewable Energy Lab in Boulder, Colorado on this technology over the last 20 or 30 years. But this is a area where we can use basically our solar energy to preheat that outside air, like I mentioned. These are typically going to be located on south facades or south-facing walls. And since it's unglazed, we have very small perforations in the material that we're utilizing. And so instead of typical fresh air intakes where we're going to have louvered sections in there, the HVAC engineers are going to design the size of the louvers to make sure that they're not going to have air velocities pulling into the building that will actually pull in rain or snow, anything along those lines. We still don't want snowflakes or rain droplets that are falling straight down. We don't want to have such a high velocity coming through those openings where it actually starts pulling moisture into the building, and then you gotta mitigate the moisture and get that out as well. So in these ones, these actually break it up into really large areas across the south-facing walls, so much larger than a typical or a traditional fresh air intake, and it has smaller openings. So the cross-sectional area of the openings of a unglazed transpired solar collector would be very similar to that of a traditional fresh air intake going into the building of the open or exposed area. It's just spread out over a much greater area. So when it pulls in, we can do this by a couple different methods. So this is a diagram of what it would look like. We have basically a plenum, so we don't want to have penetrations or use the wall cavity itself, because if we do pull in moisture or anything else, that could transmit into any of those materials. But basically, you could put a plenum material on the existing facade of that building, and you can have all of these small openings that can pull fresh air in. So at MSU, we've done studies both in horizontal and vertical orientations of this. So what we do know about Mother Nature and allowing basically how dense cold air is versus how dense warmer air is. Cold air weighs more, so it displaces and it makes basically warm air rise as it's displacing in that location. And so a good design strategy for these unglazed transpired solar collectors would be to have your intakes at the highest point of those wall assemblies, or the unglazed transpired solar collectors, because that's where you're going to maximize your temperature within that plenum area. So it's going to be pulling air in down lower to street level at the bottom of that, all the way up to the second or third floor at the top of that, and it's kind of like a chimney effect. And so we can maximize our temperature gain in these before we bring them into an air handler or a DOAS unit, and then distribute that off to our conditioned spaces. So we can look at a case study that we've been working on right now. The Norm Bjornson Hall at Montana State University. This building was completed in 2018. It's approximately about 110,000 square feet, with a variety of classroom spaces, laboratory spaces, and office spaces in there. And there's ample common spaces in there for student breakout areas, etc. And this is a LEED Platinum building, first one on the MSU campus. And when we're looking at our fresh air intake or our unglazed transpired solar collectors, the size of this is approximately 5,500 square feet of total area. So very large area. So as architects look at like, well, I don't want all of this mechanical equipment or system integrated into my building design. We'll be able to show you that, I guess, you can design these systems to be able to fit within the architecture and make it still, I guess, visually appealing or integrated as the system. So we can also pull in up to 28,000 CFM of air through these plenums. So here's an elevation view of the south facade of Norm Asbjornsen Hall, and you can see these three areas. I don't know if you can see my mouse moving on the presentation at all, but we do have two transpired solar collectors that serve as one fresh air intake on the west side, so our very far left side of the screen. We have one large one in the middle of the building, and then we have another one on the right side of the building. So three different locations. That way we could still have plenty of our glazing within all of our lab and classroom spaces, but while being able to pull in plenty of fresh air. Now, in a typical building in Montana, depending on where prevailing winds are coming from, a lot of times we're seeing our fresh air intakes are on the left side of this one or the west-facing wall. And then we'll have our exhaust side on the east-facing wall, since we have primarily winds coming from the kind of the north-west location in Bozeman. And this is what it looks like in a 3D image, kind of taken from that southeast corner of the building, looking to the northwest. You can see that these three unglazed transpired solar collectors are in these locations and work out pretty well. We'll be working on a study. We haven't done this yet, but we were looking at Jabs Hall, where we're actually using a weather station. They have a horizontal oriented unglazed transpired solar collector in that building. And so we've been recording wind direction, speed, as well as wall temperature, cavity temperatures in that transpired solar collector. And the idea behind that is do we have wind stripping effects? So if we're installing these in really windy areas, would it actually strip off some of that energy that we're trying to absorb into the black material, perforated metal, that then the air is being pulled into? Would we lose some of that? And so if you have high wind areas, one of their recommendations, if you're looking at this, is you can do a partially glazed transpired solar collector. So since it is a corrugated type material, they actually have corrugated clear glazing that could be mounted directly over portions of this. So we could, in theory, install perforated glazing on the top half of each one of these walls, and therefore we would, in effect, double our velocity being pulled in on the lower half of the wall, because now it wouldn't be pulling air in on the top half section because it would be covered with a glazing material. That has been verified to be able to increase some of your temperature increases in there. But again, if you go through that route and you're trying to minimize fan energy in a building, if you start increasing velocities in some of these areas, it's going to increase your pressure, and so therefore we're going to end up using more fan energy. So it's always a balance from the engineer's perspective of how fast can you pull air in versus what your delta T that you're going to get off of this would be. If we look at, this would be the one located in the middle of the building. You can see the mechanical penthouse up directly behind the top portion of this and to the left of it. So in the middle of the summer, this building needs cooling. So we don't want to be pulling in 90-degree air. So like on a day like today in Bozeman, it's high 70s, low 80s. And the sun would be baking on that black surface. We don't want that surface to be heating up the air that we then need to cool down with the DOAS unit. So we have bypass in the control systems where we have fresh air intake on the west side, so the left side of that mechanical penthouse located up there, that basically can pull in all of our fresh outside air equivalent Cs. So there's two different air intakes on that, and I did not include a picture here, but we can think about it from the standpoint of those two much smaller louvers that are allowing fresh air to come in, equate to the same cross-sectional area as all three of these large black transpired solar collectors that are mounted on the south facade. So this particular one, this is on the far west side because this one allows us to receive the most sunshine throughout the day. There's a parking garage just to the south of this building. There's the fitness center just directly to the west of this building. And then if I go back a slide, in the middle one, you see this, we have a bridge between the parking structure and the, Norma's Jordan Hall, that it basically will, when we have early morning sun, it's going to shade the lower half of this transpired solar collector. It's only going to pick up additional energy in the afternoons when it has direct sunlight here. So on this far west side transpired solar collector, we actually have 4 air intakes at the very top of these, and I'll show you a diagram in just a minute, but basically they're treating them as individual cavities, as chimneys, where it's going to maximize the delta T. So we have witnessed in the middle of winter, so a typical sunny January day where it could be 0 degrees Fahrenheit outside, we are pulling in close to 70-degree air in certain situations, depending on how much fresh outside air we need to be flowing through there. So therefore, we're not worrying about having to use any mechanical heating energy from the heat pumps from the DOAS unit to create a neutral air, which we're typically doing 55 degrees in this building. So even if we were pulling in 70, we would increase our air quantity in that process or blend it with our west louvers to be able to get us down to a neutral air temperature in this process. So we've had really good success in the preheating of our winter air for reducing our energy consumption in these areas. Another thing I'd like to point out, and this is something that as part of the overall oversight team at MSU for this building, we worked very closely with the architects and engineers, the whole design team, through conceptual design all the way to the finished product. And one thing that we brought up on this one that I thought was interesting is we tied in landscaping with this. And so they have trees that were part of this project that were all going to be planted just to the west side and just to the south of this location. So there's a bunch of concrete through there, but they have a bunch of locations for all of this vegetation to create a nice little common space between the parking structure and this building. Well, one thing that we wanted to look at is we want these buildings to last for a very long time. As Montana State University continues to grow, we saw challenges as they're looking at locations for new buildings. And so we have a lot of, in our area, old growth trees that are located on the campus. And when Jabs Hall was being constructed, they had to remove quite a few large trees, and there was a lot of pushback from individual student body and stuff like that about, can we relocate some of them? Trees are so large that you could only relocate certain size trees without making it, financially unviable to do that. And so in this particular application, I posed the question to the design team. I want to be able to see how tall those trees are going to be in 50 years. Are they going to be shading this this transpired solar collector? because we do get some shade in the Jabs Hall transpired solar collector from some old growth trees there. So that kind of piqued my interest on that. So they went through some simulations. So normally in the integrated design lab, we would go through some similar simulations of sun angles and shadow effects and everything else. But the architecture firm was able to do that in-house with their national firm that they were utilizing out of Seattle. And sure enough, the trees were going to actually shade a large portion of that, what they originally had picked for trees. And so they changed the type of tree in the design phase of the building, so preemptively eliminating a potential problem that we would see only decades down the road. So that is one great thing that we have about the building information modeling realm right now is we can do a lot of different simulations and work like that to optimize systems that we're going to be installing that really this system should never have to be replaced. Maybe it needs to be repainted black, but really from a structural standpoint and a performance standpoint, it will be a long life product that could be working in there. So this is what it looks like behind the scenes. And so we have temperature grids in there that we are going through and doing studies on right now to see how much temperature gain we're actually seeing and getting from operating this at different air velocities. So based on the requirements for fresh air intake for the building, how is that correlating to our chimney effect? How cold is it at the bottom temperatures versus the top ones? And then we're going to go through and report all that information out. Here is what the control system looks like from a schematic standpoint. So in the lower right corner, you can see basically our west, central, and east solar walls. So we saw those images there. We can see that we have a damper. It is showing how much CFM is currently being pulled in on the west solar wall. So this was just a snapshot at a specific application based on what they needed to get for any particular values. So we actually have a solar wall energy value on the bottom right corner there that says 58,488 BTUs is what it was actually pulling in at that given moment. And in this process, so it would measure your temperature. So it's pulling in about 31.4 degrees Fahrenheit air. By the time it is coming into the DOAS unit, where we have our solar wall damper, this is where we can actually switch between pulling in from the unglazed transpired solar collector and that west-facing solar wall. So in the summer, everything is being pretty much pulled in by that solar wall bypass. In the winter, we're utilizing the other method. Through the warranty period of the building, that I believe just was wrapping up. This is when now we can look at the data and work with the facility services folks to go through and propose changes to the control logic of this building. Because what we were seeing is there was a lot of situations where we would have been able to just increase airflow through the solar wall to drop temperatures down and still keep everyone comfortable in the building. So we could actually, kind of treat that as an economizer mode, where the initial control system and logic would actually, even in the winter, because it would be generating too much energy, it would close off the solar wall and start pulling in from the bypass on the west fresh air intakes. So these are considerations that if you're working with engineering design firms in the future and you want to put these type of systems into your projects, make sure you really coordinate and incorporate your control contractors into those discussions as well. Here's a diagram for this past January of how many basically BTUs. We're not giving you BTUs per hour. We're giving you total BTUs of what it was having, because peaks and valleys and stuff along those lines so not total consistent loads. But you can see it was a very sunny day, and on the 15th of January, where we were close to just below 600,000 BTUs of energy that were actually being available to us at that moment in time, and what we were pulling in at that application. So you can see there's great potential for energy savings here, especially on large commercial buildings. Here is another diagram that we pulled from the building management system, BMS system there, and it was showing our BTUs, but then also corresponding to what the CFM they were pulling through at any given time. And so you can see that depending on our temperatures that we were shooting for, they would adjust those accordingly. And so that'll be something that we'll be looking at a little bit more closely in the future as they go through that process of optimizing that system. So everyone always asks, how much do these systems cost? And really for this particular project, for the masonry brick system that was designed for this particular building, the cost basically was about $31.72 per square feet. And so the solar wall, which ends up taking a bunch, so they did not have to put a brick or masonry facade behind where the solar wall was located at. They were able to just go ahead and put in protective membrane and put in the solar wall directly over that. The cost of that facade was actually a little bit cheaper, $27.93 per square foot. So if you can put it into your architectural features, it actually, in this particular case, ended up serving as a cost savings for us from the building. And so that was something that, through the integrated design process, having the engineers and architects really working very closely together, they were able to make a high quality facility with reduced costs in that case. In here, there's a list of links that most of this data was pulled from in this process. And then I guess at this time, I will entertain any questions that you might have about unglazed transpired solar collectors, Norma's Bjornson Hall, anything related to that. I'm going to glance at the chat. Okay, so let me look at this. Looks like Paul posted a couple questions. How important is our solar heating gain coefficient rating on windows when designed for passive solar? Looks like there's a different couple alternative energy credits that are available out there. So on passive solar design, your solar heating gain coefficient, that's why they, in ASHRAE 90.1, they actually go through in different locations around the United States. They have different requirements based on your climate zone and type, because you don't want to just say we want a high solar heating gain coefficient for every location always. In certain areas, it's better to not have a high solar gain heating coefficient. And so it's more based on your location and if you can incorporate that passive solar. So when you're looking at how many days of the year are you going to need to be trying to take that that energy and store it passively into the walls, into the floor, coming through the windows, versus would it be better to maintain and keep out energy for 3/4 of the year, and then for that 1/4 when you actually want to go ahead and incorporate those any additional energy through the windows, that you use other strategies to make up that difference. So you really have to look at location, what the standards are via ASHRAE 90.1, and then also look at the the whole year energy production, not just based off of season. Then there's another one. Can rainwater enter the panels? Do they need cleaning on the interior of the panels? Can they be cleaned? So yes, they can be cleaned. At Montana State University, we have solar panels, or these unglazed transpired solar panels installed on, let's see, at least 5 different buildings. It is per the specs at the university now, because we get energy savings even if we have buildings blocking fresh air intake to the south, buildings located directly to the south. So these are systems that end up being really cost effective there. We actually see more rain, water, snow, moisture entering in our normal inlet, or our normal air intakes that are not transpired solar collectors, because these ones actually have a much lower air velocity going through each one of the little small slits, perforated slits. We're in a dry climate, so with the temperatures, we'd never see water collecting, and in these spaces, there's drain ports at the bottom of all of those. So if any water so if we had a big storm roll in from the south and it's raining really hard on that, any moisture that did get through that penetration would run down in that and drain out the bottom. So it's a very breathable system. Could you potentially I haven't read anything about this or seen any research done on it, but if you're looking at fresh air intakes in the Washington, Oregon, or coastal areas where it might be much more humid, if you're trying to implement this technology in those locations, you potentially could see some mold or different growth occurring there. The cleaning process for any of these, though, would have to be opening up certain cavity areas, so they'd have to remove sheet metal screws to be able to do that. They're really designed not to be a system that needs to be maintained or cleaned. So at least that's what we've seen in our application so far. There's a couple of manufacturers out there that produce these, and I bet you they have recommendations for that as well. The product that was installed in ours is called Solar Wall. So that is the manufacturer of those particular panels. Other questions? Feel free to type them in, or I don't know if you have ability to unmute yourself and I can hear your voice. That's always welcome as well. Nothing else. Okay. Well, I will go ahead and end my presentation here, and I will turn it back over to Jaya. Thank you for your time.
Thanks, Kevin.
Oh,
We'll be
sorry.
taking a
Looks like there's
5-minute break right now, and then coming back for a very short presentation on the overview of the 2018 IECC codes in Montana. So 5-minute break.
Okay.
Thanks, Kevin.
Okay, sure. Hey, Jaya, there was one more question that just popped up from Hal. So I'll go ahead and read this question and see if I can answer that. And then people can take a break now if they want, or listen to the response. So Hal says, on the material cost page, you show masonry winter conditions. I presume this is for enclosing and heating the masonry during installation that would not have been necessary during summer conditions. Is this a justifiable square footage cost? If that was eliminated, the cost would have been similar. Also, what is the construction behind the solar wall? Is there masonry behind it too? There is not masonry behind it. I'd have to look at the specific wall assembly there, but I know that they did whatever their typical backing material would be behind the, so the item that I guess I can share my screen again real quick. Maybe. Can you all see my screen? I think I unshared it. Let me share it again. So let's see. And are you able to see it one more time? I'm assuming so. The masonry winter conditions. So in this process, the brick square footage, trying to review that. So the brick facade itself, but being located in Montana, it's my understanding that they have to put different breathing conditions and stuff. So when they install all the brick facade, you got your small cavity in the back. So if moisture gets in there, there's drain locations and stuff. So I think they're looking at it from that standpoint of newer, more modern masonry conditions. I'll have to let an architect speak to the construction techniques and stuff off that a little bit better. I'm more of the heating and cooling and how those systems work, but what I know about wall assemblies, most of those, if moisture did get behind them, they do have drain locations in those spots. So I think that's a cost that we would have no matter what in most of our modern masonry buildings in Montana. That's what I think that would be from. The other thing, because if we were able to eliminate, if you're able to eliminate that, I guess it would depend on your construction technology or your type. You know, brick facade is still a pretty high quality structure. So if you're having a building of that capacity, even if they're the same cost, what you're seeing in the overall energy consumption of that building, it still goes down significantly by preheating that air. So even if the solar wall ends up being more expensive in certain applications, you may find the overall energy savings from your utility bills for heating that space would actually still be reduced. They also utilize these as straight fresh air intakes on, I know there's a Hooterite colony in Montana that actually utilizes it for one of their welding facilities. Airplane hangars as well, where you could just put this as a steel, this is your steel facade, and actually bring fresh air into that space directly from the south and exhaust air on a different side. So you could use it from that strategy too. It doesn't even have to be a ducted system that goes to a DOAS unit or an air handler. Okay, so I hope that answered your question, Hal and Paul, and I will let you go ahead and take your break now. Thanks again for bearing with me.
Thank you. Okay. Okay. And I guess we'll start in a minute. All right. This is the last set of slides that I'll be presenting. And in these slides, I will be presenting an overview of the 2018 IECC code and what to expect from the new energy code. And I'll also be opening the floor to discussion and get a feedback from the audience as to what your opinion is of the new energy code and what do you think are some of the potential barriers that you might face in implementing it. So I will try to go over these slides very quickly and get to the questions that we have prepared for you. When you answer the questions, I have the option of you either being unmuting yourself, or I have prepared certain Padlets so that you can write your opinions on those Padlets. So let's see which system works better when we reach there. Okay, so here's an overview of the presentation itself, and I'll first present an overview of the code adoption process in Montana, and then either me or Carl will be providing some details on this process and where we are at right now. I'll then be providing you with the highlights of the changes in the commercial sections of the 2018 IECC. I just want to reiterate that this is not a comprehensive section by section review, which I am sure that you heard about already in the last code conference. But this is like a general overview of what changes affect us in Montana. And finally, I will be opening the floor to discussion. I do have a few questions that I want to pose to the audience so as to structure your comments and your feedback. And hopefully we can get some fruitful discussion started with regards to the status of the energy codes in our state. So here's an overview of the code adoption process in Montana, and the rules have been drafted, but it has been some months since we have seen the draft. Carl, would you like to say a few words on the adoption process and where we are?
Sure. I haven't checked for the last couple of days, but right now the draft of the 2018 code with the Montana amendments, it's in the legal counsel's office at the Bureau of Labor and Industry. And after their review, it'll come back out for more public hearings. So you can find this on I was kind of looking in this chart where that would be. So from our information, we think that should be coming out anytime. So we can see a draft of what's going to be there. But we don't expect adoption probably until much later on in the year, because there's still several steps to go through, as you can see. So that's about all I know right now. If there may be others that have kind of kept a closer look on it that may have more information.
Okay. Thank you, Carl. Here are some of the key changes to the commercial sections of the IECC. What we see is that HVAC, the section on HVAC, the section on water heating, the section on lighting get major upgrades. And the specifications of lighting systems have also received an energy efficiency boost. Now, we also have additional sections for efficiency package options that you need to comply it when selecting the prescriptive path of the code, with 2012 IECC having only 3 efficiency package options, while 2018 IECC has up to 5 efficiency package options that you can select from. We also have certain increased stringencies in the requirements for commissioning. And finally, new to the 2018 IECC is the appendix that articulates the requirements for solar-ready buildings. So here is the compliance path, or here are the different options or the different compliance paths that you would follow if you are using the 2012 IECC. And in this code, you could either comply with the ASHRAE 90.1 2010, or meet the prescriptive requirements of the envelope mechanical systems, the service hot water heating systems, and lighting. And in addition, pick one of the 3 high efficiency options to implement, or meet the performance requirements of the code, which would include compliance with the performance path articulated in the code and a number of other mandatory requirements such as air leakage and such as mandatory requirements for service hot water heating and lighting. Now, fast forward this to 2018 IECC. You can now either comply with the ASHRAE 90.1 2016 or meet the prescriptive requirements of the envelope mechanical, service hot water heating and lighting, and in addition pick one of the 8 high efficiency options available in the code to implement, or meet the performance requirements of the code. So a major change in the section on building mechanical systems in the 2018 IECC was a major reorganization of the section. And rather than having separate mandatory and prescriptive sections, as was done in the earlier codes as well as in the 2012 IECC, requirements are now grouped together under sectional groups. So in this arrangement, similar requirements are grouped together. For example, section 403.4, which is dedicated to controls, has mandatory requirements for controls, prescriptive, as well as performance specifications for HVAC controls. While on the other hand, 403.5 is now dedicated to the mandatory, to the prescriptive, and to the performance specifications for economizers in the code. Other highlighted additions in the 2018 IECC are the mandatory requirements for heated and cooled vestibules. Now we are required to provide a thermostat control in a heated vestibule that should be configured to turn off the system serving that space at temperatures or at outside air temperatures that are greater than 45 degrees Fahrenheit. We also have mandatory requirements for providing demand control ventilation for spaces that are greater than 500 square feet. And in addition, there has been increased stringencies in the efficiency requirements for certain type of HVAC systems, which include packaged terminal air conditioners, which include warm air furnaces, gas and oil fired furnaces, and heat rejection equipment. Now, economizers in the 2018 IECC have much more stringent requirements for their implementation, and the code has retained those trade-offs with higher efficiency cooling systems. However, a number of other climate zones are included now in the code. Also in the 2018 IECC, we have a mandatory implementation of a fault detection and diagnostic system for air-cooled unitary direct expansion units and VRF units equipped with an economizer. We also have lighting updates, and we have talked enough, I think, about lighting in our prior presentation, but here's a summary of all the changes that you will see on the implementation of the 2018 IECC, and some mandatory requirements include requirements for both interior and exterior lighting, which include reduced lighting power densities and certain mandatory controls or mandatory language for the use of controls. As I mentioned earlier, in order to comply with the prescriptive section of the code, we have to meet the prescriptive requirements of envelope mechanical, service hot water heating, and lighting. And in addition, pick one of the 8 high performance options to implement that are offered in the code. Now, in addition to the 3 existing high efficiency options that have been written in the 2012 IECC, the new efficiency package options include digital lighting controls, include dedicated outdoor air systems, reduced energy use in service hot water heating systems, enhanced envelope performance, and reduced air infiltration. It is now mandatory to conduct commissioning for certain types of buildings. And it is now mandatory to provide the owner with information about O&M of the building systems. Now, in other words, how the building systems and equipment are intended to be installed, how they are intended to be operated, and how they are intended to be maintained. There is also a requirement to have commissioning compliance checklist for the preliminary commissioning report. And the list of requirements in that checklist includes commissioning plan, results from system adjustments and balancing, O&M manuals, etc. And the checklist also ensures that commissioning has been executed for all the required systems. And also the checklist requires information on when follow-up testing is going to occur. Also, we have a section in the 2018 IECC that has a separate that is separately described for the commissioning of lighting systems. And in the 2018 code, that commissioning of lighting systems has become mandatory. We also have a new chapter that provides some clarity for compliance of building renovations, alterations, repairs, and occupancy change of existing buildings with the energy code. And essentially, this chapter points to parts of Chapter 4 in order to, Chapter 4 is the energy efficiency chapter, in order to demonstrate compliance. And I would like to point to one section in this section of the code, or rather an exception to this section, is that according to this particular section right here, 503.6, lighting systems, new lighting systems that are a part of the alteration shall comply with Section C 405, section on electric power and lighting systems. However, there is an exception for this requirement, that is alterations that replace less than 10% of the luminaires in the space, provided that such alterations cannot, do not increase the increased lighting power. So in the past, this particular exception was for 50% of the fixtures, but now it has come down to 10% of the fixtures. And finally, some jurisdictions may require solar-ready zones in order to encourage the installation of renewable energy systems. And the 2018 code provides some recommendations to prepare buildings for future installations of solar energy equipment, piping, and wiring. And with that, I would like to engage the audience with some questions about your opinion of the code. And let me see if I can pull up the Padlet screen real quick and share the, I don't know how the system is going to work with you, but let's give it a shot. Okay. Okay, so do you see my screen? Okay, so I'm going to share this link with you in my chat session. Let's see if I can get the chat thing to work. Okay. To everybody. So do try to log on to this, or try to click on this link. And once you click on this link, this particular screen will appear on your screen, and then you have to add, and then you can type in your questions, answers, or comments here. I don't know if this is a better way, or if you would like to unmute yourself. Anything would work. So the first question is, are there particular provisions in the code that are difficult to adopt in the industry? Are requirements for commissioning too stringent? Is there a resistance to adherence for the EEMs and other topics that you may wish to discuss? Does anyone want to say something about it? Or so someone said lighting. Okay, so someone's writing some comments. Or would you like to rather be unmuted and talk to the audience?
Just to remind everybody, you probably do have the ability to unmute yourself. If not, let me know in the chat and we'll fix that.
Sure. Yeah, I think this is taking a little longer than I expected. I think unmuting is much better.
Oh, this is David. I just had a quick question on lighting, and it was specifically related about pulse width modulation versus current control. And I was wondering if you know what the market penetration of those two different technologies are.
You
and,
mean
the benefits of either one?
could you repeat your question again?
It relates really to the power control for lighting control, if it's pulse width modulation or current control. And my question is if you might know the market penetration of those two different technologies. I think that current control is usually used when you want to dim to very low levels for architectural applications. And that is not as effective for pulse width modulation.
I'll take this question and can I answer you at a later time?
Yes, yes.
Okay. That's David. David Lemieux. Okay.
Yeah, thanks.
Okay, so we do have some comments out here. The first one is commissioning is a great idea. The cost of the EEMs are always a heavy lift for the clients. The other comment is commissioning should define what is a qualified commissioning agent and certified agent versus uncertified agents. Does anyone have any more comments, concerns, questions about the particular provisions in the code and that make it difficult to adopt it in our current industry? No. All right. Let's move on to the next question, which is, are the jurisdictional enforcement consistent across the state? Does the audience have any stories, problems, or solutions to some of the enforcement issues that they have faced? And for that, I do have another Padlet ready for you. Let me see if I can pull it up real quick. Or would you rather unmute yourself and talk to the audience? Either or would be fine. No comments about whether jurisdictional enforcement is consistent across the states, or do you have any issues that you have come up with implementing the code? Or oh, sorry about that.
Jaya, it looks like somebody's writing, but could you just briefly say how the commercial code is usually enforced across Montana? By what entities and how often?
I think it's usually enforced in the cities, and you can't really do much about it outside those jurisdictions.
So it's the same.
Exactly. It seems like
Same.
rural Montana is more lax. Exactly.
Yeah, this is the same thing, and I deal mostly with the residential code, so same type of issues.
Yes. Has there been, and there is a question from Paul Cheeder to me, has there been any Montana studies on commercial code compliance? Paul, do you mean how many buildings have been complying with the energy code? Do you mean a kind of review of the number of buildings? Or do you mean how much savings is achieved on implementing the commercial code in the state? Paul, Paul's response was overall compliance with all issues of the code. Paul, as of now, I have not seen any studies, but I could spend some time looking for any information that I get. If I do, I will forward it to you. On another note, NIA has come up with certain documents and publications that actually talk about certain issues about code implementation in Montana. And I could forward those documents or those articles or those reports to you. So we do have some information that has been compiled by NIA. So my third question is, are there any high performance technologies that were not covered in this presentation that you know of, high performance technologies that worked well in the state? I will once again try and send the link to you first if you have any comments. Wind collection. Okay, that's a good one. Especially, yeah, that's actually a very good one, especially in the eastern part of our state. What else? Okay, it seems that wind collection is one of the things that we could think about for our future presentations. James has, okay, pump storage. Would that mean using elevations to store water and then use that elevation to generate energy? Okay. Okay. Yes, we could definitely look at that. Anything else? There was a comment, renewable energy storage in general. Can you give us some examples about renewable energy storage? Things such as batteries, pump storage, even geothermal fields could be used to store solar energy during winter time. Okay. Okay. And we have, is MSU interested in researching other alternatives not yet commercially available? Well, we are a research institution, so yes, of course. And then we have another question from Paul Cheetah, who is asking, can it be assumed that a Montana engineer or architect stamp on the plans means the plans meet the energy code? Paul, I think the answer to your question is a little more complex than yes or no, because the engineer or the architect needs to refer to their resources, which could include building officials, which could include their own energy calculation methods that they use, or their methods or their protocols that they use to make sure that those protocols comply with the requirements in the code. Combined heat and power as high performance. Now that is another very complex issue, because combined heat and power means that you are moving your energy consumption to fossil fuels. You are utilizing gas, you are utilizing oil to generate electricity and heat. So that is slightly controversial, because you are now moving your energy resources from electricity to something that is a fossil fuel. Okay. Does anyone have any more comments, concerns, questions? Um, Okay, our very last question is that are there tools, educational outreach programs that currently assist you with compliance? And for that, once again, I will copy the questions web link. So are there tools, educational and outreach programs that currently assist you with compliance? Does anyone have a comment here?
I don't know if others didn't get the link. I didn't see the link in the comments, Jaya.
Oh, I think I sent it to Paul only. Okay. ComCheck is one of them, yes. Could you elaborate on how data loggers, you are using data loggers to assist you with compliance with the code? Could you unmute yourself and talk a little more about it?
So I'm just using electrical or just current transducers, then measuring voltage and then recording over time. And with the variability of code controls, particularly in lighting, it allows you to log what loads you're actually, what the actual loads are over the course of a day, a month, or so forth. And that also accounts for daylight harvesting and just different user preferences. That makes sense?
Yeah, it does. But how does that help with the compliance?
Probably only in the sense that it really shows you, particularly like if you, well, this kind of comes in maybe another question I would have, and that would be really one of what your lumens are. So maybe really what you might want to do, I kind of favor this approach to over illuminate a building and then just put a high trim on your controls. And then when you get to a certain lumen depreciation, you can come back and you have some bandwidth there so you can step it back up.
Okay. Paul, you mentioned ComCheck for your compliance, or a tool that you use for compliance. Can you elaborate on that, and do you see any issues using ComCheck for compliance? Okay, I guess, okay, so Paul has responded, and I'm going to type in what Paul has said. ComCheck is free. I believe that many plans are submitted with it. Do you see any restrictions or any restrictions using ComCheck, or any problems? Especially when you want to comply with the Montana code. Okay, so it has, okay, so these are some really useful comments right here. We have, these have been effective, easy to understand, but not for complex systems. Okay, I guess for complex systems, you may need to move over to customized energy models to, and the performance path to make sure that your building complies with the code. How many of you use energy modeling in the state? Okay, we have the use of eQuest. So let me see, energy. eQuest is one of them. Does anyone use Energy Plus? Okay, so Carl has used a combination of eQuest and Carrier HAP for energy modeling. Has anyone used eQuest? David has said that it is difficult to get engineers to do modeling on projects. Does it mean that you have to outsource it to out of state and energy modeling groups? Okay, Cushing Terrell uses energy models on several projects. We use Energy Plus, eQuest, and TrainTrace. I think especially with high performance buildings, one should go the performance route and use energy models. I think the reason why they are reluctant is because it takes a lot of time. It takes a lot of time, and the answers are not always, and you need a lot of time to calibrate the model to get the model to perform the way it should perform with all those complex interactions between the different systems. Exactly, owners don't like to pay for it. Owners don't like to pay for that extra step that they have to take to ensure that their buildings is high performance. But what I think is important to understand is not only how the building is designed, but also how it performs in order for it to qualify as high performance buildings. And that includes evaluating the performance of your design as it was planned or designed, and as well as to enforce a good operation and maintenance practice in place for the high performance building. Oops. Okay, so I guess these were the 4 questions that I wanted to ask the audience, and with that, I will conclude my presentation. So we do have our contact information on these slides right here, and all of these slides will be available on NCAT's website for you to refer to after this presentation. Thank you very much for your time, and thank you very much for participating in this presentation. Thank you.
Thank you very much, Jaya.
Thank you.